Polarization of waves. Imagine we have a rope which is being vibrated in this plane, and so on. It would produce transverse waves heading in this direction, aligned like this black wave, the red wave, the blue wave, and any other number of alignments of wave. If at this point we had a slot with a vertical alignment, you see that the red wave and the blue wave would be unable to pass through. But the black wave, as its vibration is in line with this slot, would pass through. If we then had a second slot up here, aligned at 90 degrees to the first slot, the black wave could not get through. The material Polaroid acts rather like these slots for the visible part of the electromagnetic spectrum. One piece of Polaroid, aligned at any angle, will reduce the amount of light getting through, as it only allows the light which is aligned in one particular direction. A second piece of Polaroid, aligned in the same direction as the first, will not change the amount of light getting through. But if the second piece is perpendicular to the first piece, no light will pass through. Transverse waves can be polarized. This is because the vibration is at 90 degrees to the direction of travel of the wave. However, longitudinal waves, such as sound waves, cannot be polarized. Their vibration is parallel to the direction of travel. Light waves are generally produced in random planes, but can be partially polarized by reflection off glass or water. Polaroid sunglasses are very effective at reducing glare from sunlight reflecting off water. Molasses Law. If we have two sheets of Polaroid, the first will polarize the light. That's this one here we call the polarizer. So we have randomly orientated light coming in and polarized light in the vertical direction coming out. The second sheet, the analyzer, has the same alignment, and so all the light will pass through. However, if the second piece of Polaroid is at an angle theta relative to the first, the amplitude of the light passing through the second piece of Polaroid will be the component of the amplitude at an angle theta of the light entering the analyzer. If the polarized light entering the analyzer has an amplitude x, the amplitude of the light leaving will be x cos theta. The intensity of a wave is proportional to the amplitude squared, and so the intensity leaving the analyzer will be equal to the maximum intensity of the light entering the analyzer times cos squared theta. This is known as Molasses Law, and you are expected to remember and be able to use this equation. I've copied Molasses Law again here. When theta is equal to 0 degrees, the cosine of theta is 1, and so intensity is equal to the maximum intensity entering. The Polaroids are aligned, and all light passes through. When theta equals 90 degrees, the cosine of theta is 0, and so the intensity will be 0. The Polaroids are crossed, and no light passes through.